Okay, so this mini lecture is going to look at the normal force really quickly. It's not going to be very long, but I want to identify some very important features about the normal force. So we introduced the normal force in a sort of just a general overview of some of the forces that we're going to use. And I want to make sure that we really embrace what the normal force is. Some of the important things about the normal force that we've already said is that it's a contact force. It is solely the result of contact. And this is important because if there is no contact, there is no normal force. Now, we often think of that contact as sort of a resting contact. Indeed, when I push on an object, I'm in contact with it, but I'm going to identify that pushing force as something very specific. This is as opposed to if an object is, let's say, resting on something. So if I have the eraser resting on my hand, that contact exists because of the position of this eraser relative to my hand. So this would be an example of a normal force that we're going to look at. Now, we said that the normal force was the result of that contact and those molecules getting squished and wanting to push back, right? But there's some other features about the normal force that we want to make sure we understand. So we first have to appreciate that the contact exists and it's contact between two very specific objects. So let's say that we have a block of wood sitting on a table. Just looking at the normal force only, the block of wood is in contact with the table. And therefore, because of that contact, a normal force exists. If the block of wood is sitting on the table, it's squishing the table, and the table is pushing back in the upward direction. That normal force is the result of the block and the surface, the table. What if I take that same surface and I put it on an incline? Now the block of wood is sitting on the incline. How does the normal force look for a block of wood on an incline? Well, there's still contact between the wood and the surface. So there's still a normal force between the block and the table. What about the direction? If I'm squishing the molecules this way, they want to push back that way, perpendicular to the surface. So they're pushing this direction on the block. And again, this is between the block and the table. Pushing as if I were going to squish this way, they're going to push back that way. Let's take this to an even more extreme. What if the block is being pushed against a wall? Now, that's not going to just sit there, obviously, but let's say there's a force being applied to hold that block there against the wall, so pushed up against the wall. What about the normal force in this case? Well, the block of wood is pushing in contact with the molecules in that direction, so the molecules of that wall are pushing back in this direction. Again, between the block and the surface, and we tend to think of a surface like this more like a wall. All right, well, what do we notice about these three seemingly similar scenarios where we have a block in contact with a surface? We should notice, and the word normal is sort of a clue to that, that force always acts perpendicular to the contact, and that's what's important. A normal force is indeed the result of contact, and it acts perpendicular to that interacting surface. So whenever we want to draw a normal force, if we're on a horizontal, the normal force is always going to be vertical. If we're on a vertical, the normal force is going to be purely horizontal. And if we're on a slope, the normal force is going to be perpendicular to that slope. So very important features of the normal force. They're reactive is the final thing that I want you to be thinking about. They're only as large as they need to be. So it truly is the force between the block and the table. So in this example, if I'm looking at the forces on this green block, if I add another mass on top of the green block, well, then that interaction between the green block and the table goes up. There's another force acting down. There's more contact in terms of squishiness on that surface. So the normal force between the block, same table, is going to increase because that contact has increased. That squishing has increased as a result of adding something on top of it. But we're still only concerned about that surface-surface interaction. Similarly, if I were to take a rope and pull a little upwards, maybe on this block. So let's say I'm sliding this block along the ramp, but I'm pulling upwards on it. Well, then I'm alleviating some of that squishing that's happening on the ramp. If I'm pulling a little up on the block, not coming in and staying in contact, I'm not pulling the contact away, so there's still contact, but it's a little easier to pull it if I pull it up because that contact now has been lessened. So my normal force would decrease in that case. I'm adding a little more force in the upward direction in the same direction as that normal force, and so my surface-surface interaction doesn't need to be as much. I'm not squishing the molecules as much. So the normal force is reactive. It's how much it needs to be when, or how much it is as a result of that squishing. More squishing, higher normal force. Less squishing, less normal force. All right, 3 important pieces of that normal force as we use them and draw them on our free body diagrams. They don't exist if there's no contact. If there's no contact, there is no normal force. So we want to keep that in mind, and then how that normal force looks perpendicular to that surface. All right, good job.